Hello everyone, today we are going to cover measurements and mechanics as part of the first chapter in Bushong. The objectives for this part of that chapter would be to discuss various scientific systems of measurement, list the three systems of measurement, and then identify the 9 categories of what are called mechanics. So in physics, there's various categories of physics. And in radiography, physics is principally limited to the study of two of them. So in our study of physics, because like it says here, there's many different categories of physics. An example would be astrophysics, for example. But we're going to be focusing in on mechanics and then electromagnetism. So when we're talking about measurement, and this is what is talked about in the first chapter, physicists strive for certainty and simplicity when experimenting and drawing conclusions. And in mechanics, there are only 3 measurable, what are called base quantities. We've got mass, we've got length, and we've got time. In your book, if we're looking at Bushong and we're looking at the 11th edition, it's on page 13 down at the bottom. And you can see that there is a temple, basically, a Greek temple. And at the bottom, you can see that it says length, mass, and time. And that's the base. And then from that, then you can see that in the columns, you've got all these various things like energy, power, work, momentum, and so forth. Those are what are called derived quantities that come from the base quantities. And then the top of the temple, in our field, there would be some special quantities like exposure, dose, effective dose, and radioactivity. So as I just mentioned, combinations of the base quantities form what are called the derived quantities. So from the mass, length, and time, we can get energy, work, power, momentum, force, velocity, and acceleration. If you look to the picture to the side, the space shuttle blasting off into space is a great example, really, of all of those. Okay, energy to get the rocket going. When energy is done, work is expended. As power is expended, momentum comes into play. There's a force that pushes the rocket off the launch pad, and then it starts going very fast. And this is where velocity and acceleration come into play. As I mentioned, then we've got special quantities of measurement. And in radiology, these would include exposure, dose, dose equivalent, and radioactivity. Let's talk first about mass. So in science, in physics, the unit of mass is the kilogram. Okay, so whenever we talk about mass, we talk about the kilogram. It has a very precise definition. It's the mass of 1,000 cubed centimeters of water at a very precise temperature, 4 degrees Celsius. So why does it have to be so specific? Well, basically, if you wanted to know what a kilogram is anywhere in the world, and if you had 1,000 cubed centimeters of water and then you froze it to or cooled it to 4 degrees Celsius, well, now you'd have a kilogram. There's an actual prototype of the kilogram. This is in Paris at the International Bureau of Weights and Measures, and that is what is the accepted kilogram in science. There's a picture of it there. Length. The unit of length is the meter. And it was originally defined by the distance between 2 engraved lines on a platinum iridium bar that once again was kept at the International Bureau of Weights and Measures in Paris. If we look at the bottom, the international standard unit of length term the meter is approximately equivalent to about 39.37 inches. Remember, in the United States, we use the British system. Most all of the world uses the metric. So to give you a comparison, then the meter is 39.37 inches. Now, in science, once again, you want to be very exact. So the meter was redefined in 1983 as the distance traveled by light in a vacuum in almost 1/3 millionth of a second. It's a pretty small amount of time there, but how far light can travel in that distance. The unit of time is the second, and it was originally defined in terms of the Earth's rotation, which is a fraction of what's called a mean solar day, mean meaning an average solar day. It's now based on the vibrations, though, of cesium atoms in what's called an atomic clock. So if we look at the picture there, that looks nothing like a clock like we think of a clock, but the NIST-F1 is the nation's primary time and frequency standard, a cesium fountain atomic clock developed at the NIST laboratories in Boulder, Colorado. NIST-F1 contributes to the international group of atomic clocks that define Coordinated Universal Time, or UTC, the official world time. Because NIST-F1 is among the most accurate clocks in the world, it makes UTC more accurate than ever before. So time is based on the vibration of cesium atoms. Now, when we talk about measurement, every measurement has two parts. You've got something called magnitude, and then you have a unit. Okay, so in this example, 100 is the magnitude, and then centimeters would be the unit. And we've got four systems that we can use to represent the base quantities. We've got the MKS system, which stands for the meter, the kilogram, and the second. The CGS, which is the centimeter, gram, second. The SI, which is Systems International, the meter, the kilogram, the second, and any derived quantities. And then the British system, which is what we use here in the United States, the foot, the pound, and the second. So as I mentioned, in almost all of the world, the metric system is used. So if we read, the metric system was developed in France during the Napoleonic reign in the 1790s. The scientific community adopted the metric system almost from its inception. The metric system missed being nationalized in this country by one vote, just one vote in the Continental Congress in the late 1700s, early 1800s. And the United States still uses the British system. Remember, we were a British colony. The British came over. The British then, during our independence, they left, but their system still stayed. When we look at this map down here of the world, 3 nations have not officially adopted the International System of Units, the metric system, as their primary or sole system of measurement. You can see, of course, the biggest one is the United States, and then you've got 2 little tiny countries, Liberia and Myanmar. All the rest of the world uses the metric system except Liberia, Myanmar, and then the United States. Let's move on to mechanics. Mechanics is a segment of physics which deals with objects at rest and objects in motion. So mechanics is objects at rest and objects in motion. So here we've got a picture, space shuttle sitting there at the launch pad. Now rockets fire up, and now we've got an object in motion. The first one is velocity. Velocity is a real fancy name for speed. Okay, sometimes called speed, it describes how fast an object is moving. The precise definition is the rate of an object's change of position with time. Now, in this physics, we need to memorize the formula and we need to memorize the unit. Okay, this could be on the registry. We need to remember that velocity is distance divided by time. A distance divided by time. And then we would get to velocity, and its unit would be the meter per second. Average velocity. So during your trip to school today, well, we're in COVID time right now, but anyways, if you were driving to school, there may have been times that you were stopped and at other times that your speedometer was reading 50 miles per hour. Yet on average, you were moving, for example, with a speed only of about 25 miles per hour. Okay. So the unit for average velocity is also meter per second. So how do we calculate the average velocity? We take the initial velocity plus the final velocity, and we divide it by 2. And when we do that, then we get the average velocity, whose unit is meter per second. Acceleration. What does it mean to accelerate? Well, acceleration describes how quickly or slowly the velocity is changing. Okay, like when you push the accelerator on your car, you go a lot faster, right? Describes how quickly or slowly the velocity is changing. Its unit, a little bit different, meter per second squared. So the unit for acceleration is meter per second squared. To calculate acceleration, we take the final velocity minus the initial velocity, and we divide it by time. So VF minus VO divided by time. Let's move on to what are called Newton's laws of motion. Okay. Well, first of all, a little bit of history and who Newton was. Newton was an English physicist. He was a mathematician. He was an astronomer, a natural philosopher, and an alchemist. His Treatise Philosophiae Naturalis Principia Mathematica was published in 1687, and it described universal gravitation and the 3 laws of motion, which laid the groundwork then for what we call classical mechanics. His work dominated the scientific view of the physical universe for the next 3 centuries, and it's still the basis for modern engineering today. So, brilliant man, brilliant scientist, and we're still using what he came up with today in engineering. Let's take a look at Newton's first law of motion. So a body will remain at rest, or it will continue to move with constant velocity in a straight line unless acted on by an external force. So a great example of this is the sun and the planets. Right? So if we take planet Earth, the third planet from the sun, we are in a certain or at a certain distance from the sun. And we stay there because of the gravitational pull of the sun on planet Earth, but also the Earth is traveling. It's got some velocity, not some, it's got a lot of velocity. But the combination of those two then allow it to stay in its orbit. Now, if the planet Earth, did not have the gravitational pull of the sun, let's say for some reason gravity shut down and there was no pull on the Earth, planet Earth would, instead of going in this circular orbit, would fly off in a straight line. And it would keep going theoretically unless it was acted on by another external force. Maybe it hit an asteroid, maybe it encountered the gravitational field of another planet, but it would just keep going in a straight line. So a body will remain at rest or continue to move with constant velocity in a straight line unless acted on by an external force. Newton's second law. Newton's second law has to do with force. The force acting on an object with acceleration is equal to the mass multiplied by acceleration. So here's another formula that you must memorize. F equals ma. F equals ma. Force is equal to mass, the mass of an object, multiplied by its acceleration. The unit for force is the Newton. So F equals ma. SI unit for force is the Newton. So when you do the math, multiplying the mass times the acceleration, the answer you would get then would be in newtons. Newton's third law has to do with action and reaction, and you probably have seen this. This is called Newton's cradle. And for every action, there is an equal and an opposite reaction. So look at the balls here. You pull the ball a certain distance away from the other balls on the other side. It hits it, and then it moves that same amount of distance. Equal and opposite, okay, in the opposite direction. If you've ever played with one of these, if you took then two balls and pulled it, then two balls then would go off in the opposite direction, but with the same or equal amount of distance that you pull the other balls. Weight. We had talked a little bit about weight before, and we said you can't have weight unless you've got gravity. So a force on a body caused by the downward pull of gravity on it. So weight is equal to the mass of an object multiplied by g, which is the acceleration of gravity. Okay, the gravitational pull on wherever you're at, planet Earth, another planet. Okay, the gravitational pull. Okay, weight equals mass times the acceleration of gravity. Well, what is the acceleration of gravity? The acceleration of gravity, because mass affects both the force of gravity and the resistance to accelerate, all objects end up falling at the same rate. Okay? So no matter what object you have, it's going to fall, if you lifted it to a certain distance, at the same rate. Now, we have to take some things into account. There may be air resistance based on the size of the object, but if you had just a certain quantity of mass, and then you had a bigger amount of mass, it's going to fall at the same rate. So at our distance from the Earth's center, using the mass of the Earth, we get an acceleration of, and this is important to memorize, the acceleration of gravity on the Earth is 9.8 meters per second squared. 9.8 meters per second squared. The ratio is sometimes called the gravitational field strength, and it's expressed as 9.8 newtons per kilogram. The gravitational field strength is a property of the Earth's gravitational field and not a property of the baby elephant in this case, or the mouse. All objects placed within Earth's gravitational field will experience this amount of force, 9.8 newtons, upon every 1 kilogram of mass within the object. Being a property of the Earth's gravitational field and not a property of the free-falling object itself, all objects will experience this amount of force per mass. As such, all objects free fall at the same rate regardless of their mass. That's a very, very important statement. All objects free fall at the same rate regardless of their mass. Because the 9.8 newtons per kilogram gravitational field at Earth's surface causes a 9.8 meter per second acceleration of any object placed there, we often call this ratio, as I mentioned, the acceleration of gravity. So, suppose that an elephant and a feather are dropped off of a very tall building at the same height at the same time. Suppose also that air resistance, and this is important, air resistance could somehow be eliminated such that neither the elephant nor the feather would experience any air drag during the course of their fall. The question is, which object then, the elephant or the feather, would hit the ground first? The animation at the right accurately depicts the situation. The motion of the elephant and the feather in the absence of air resistance, so it would be in a vacuum basically, is shown. Further, the acceleration of each object is represented by a vector arrow. Many people are surprised by the fact that in the absence of air resistance, the elephant and the feather strike the ground at the same time. Momentum. Momentum is represented by lowercase p. So whenever you see lowercase p, it stands for momentum. So the product of the mass of an object and its velocity is called momentum, represented by lowercase p. P equals mv. So momentum equals mass multiplied by velocity. The greater the velocity or mass that an object has, the greater is its momentum. The greater the velocity or speed, or the mass, heaviness, that an object has, the greater is the momentum. A boulder accelerating down a hill gains momentum as its velocity increases. Law of conservation of momentum. The total momentum before any interaction is equal to the total momentum after the interaction. So take a look at the two spheres here, the two balls. Look at A before collision, then they collide, and then notice after collision, it's the same momentum, the same velocity. Work. The work done on an object is the force applied multiplied by the distance over which it's applied. So, formula to memorize, work equals force times distance. Work equals force times distance. And it has a rather unique unit. The unit for work is called the joule. So if you take a look at the example, well, when you drop a book, okay, you've lifted it to a certain height, and then you let it go. The book's weight pulls it back down. What pulls it back down? The force of gravity pulls it back down, and now you've got work. Power. Power is the rate of doing work. Anytime we see rate, we're going to talk about a time factor. So power, capital P, is equal to work divided by time. Power equals work divided by time. Or we could say, what is work? Well, we learned that work is force times distance. So we could also say that P is equal to FD, force times distance, divided by time. The unit is joule per second, but we usually refer to the unit of power as the watt. Now, in the British system, we use the unit for power as horsepower. You think about that like a car. A car has its engine has a certain amount of horsepower. But what is horsepower? Horsepower is 746 watts. That's kind of a strange number. And how did we come up with that? Well, before we get into that, 1,000 watts equals 1 kilowatt. Remember, kilo, K-I-L-O, is that prefix meaning 1,000. So 1,000 watts is 1 kilowatt. Now, the story of the horsepower, the story goes that James Watt, hence the term watt, okay, was working with ponies lifting coal at a coal mine, and he wanted a way to talk about the power available from one of these animals. And he found that on average, a mine pony could do 22,000 what are called foot-pounds of work in a minute. He then increased that number by 50% and pegged the measurement of horsepower at 33,000 foot-pounds of work in 1 minute. So if we look to the side there, 1 horsepower is 33,000 foot-pounds per minute. Name actually comes from the work that a horse did. Energy. Energy is the ability to do work. And there's two forms of mechanical energy. And this includes potential, or stored energy of position, and then movement, which is the energy of motion, kinetic energy. Take a look at the ball swinging there, look at the total energy, and notice how it changes, having potential energy when it reaches the top, then it starts to swing for kinetic energy, and back and forth, always giving you that total amount of energy. There are a couple of formulas for energy. The formula for kinetic energy, 1/2 times the mass times the velocity squared, or 1/2 mv squared. Potential energy has a formula as mass multiplied by the acceleration of gravity multiplied by a certain height. So PE equals mgh. Potential energy is mass times the acceleration of gravity, and you can see in the drawing there, lifted to then a certain height. Heat. Now, when we talk about heat, we're talking about the kinetic energy of the random motion of molecules. So the more rapid and disordered the motion of molecules, the more heat an object contains. So think about water, and when that water is boiling, okay, what's happening? It's moving all over the place, right? It's a random disordered motion, The unit of heat is called a calorie, and it's defined as the heat necessary to raise the temperature of 1 gram of water through 1 degree Celsius. So the unit of heat, the calorie, heat necessary to raise the temperature of 1 gram of water through 1 degree Celsius. Now we can transfer heat in different ways. You've got a fire going, heat rises, convection. If I put a poker into the fire, poker's going to get hot, conduction. Or the heat then is given off as radiation. So in these two pictures, you can see that. Here's also a pot of water. Okay, you've got the radiation coming off of the heat. The pot handle could get hot, conduction, and then convection is occurring then within the water itself. So the three ways that heat is transferred are conduction, convection, and radiation. Temperature. So there is more than what is listed here, okay? But these are the main three ways that we measure temperature, okay? All over the world, except those three countries that we talked about, the United States included, they use Celsius, okay? But here in the United States, we use Fahrenheit. And in the scientific community, we use Kelvin. Your book gives you these formulas, but you can see there's a little depiction here of how to go from Celsius to Fahrenheit to Kelvin. R would stand for another unit, Rankine system of measurement, but we're not going to talk about that. But I would like you to make sure that you look at, in your textbook, the formulas for converting temperatures from Celsius to Fahrenheit and Fahrenheit to Celsius. So if you wanted to find the temperature Celsius, you would take 5/9 and multiply it by the temperature Fahrenheit minus 32. If you wanted to find the temperature in Fahrenheit, you would take 9/5. So you take the reciprocal of the temperature in Celsius and you'd add 32. And then if you wanted to find the temperature in Kelvin, you'd take the temperature in Celsius, and to that you would add 250. and 73. So these formulas are in your book, in the 11th edition of Bushong. It is on page 20. And also figure 117 is important. It gives you some important daily things. Figure 117, boiling point of water, 100 Celsius, 212 Fahrenheit. Room temperature, freezing of water, 0 Celsius, 32 Fahrenheit. And then something called absolute zero. Now, absolute zero means that if you get to this temperature, there's absolutely no motion of the molecules. You've frozen it totally solid. Okay, that is minus 273 Celsius, which is minus 459 Fahrenheit, or absolute zero is 0 degrees Kelvin. So, some temperature facts. Where was the coldest recorded temperature on Earth? Antarctica. Antarctica is the coldest place on Earth with the lowest natural temperature ever recorded of minus 90 degrees Celsius or minus 131 Fahrenheit at the Russian Vostok station in 1983. Well, what about the hottest recorded temperature on Earth? The biggest scorcher ever noted was on September 13th, 1922 in El Azizia, Libya, when the mercury hit 136 degrees Fahrenheit. El Azizia is near the Sahara Desert. So look at that extreme, going from minus 131 Fahrenheit to 136 degrees Fahrenheit, coldest and hottest temperatures.